So welcome to the Picture Language Seminar. Today we have a very interesting talk. Antti Kupiainen in Helsinki is going to tell us about integrability of the Liouville equation. Antti can look at the picture behind me of the building where I'd like to be and where Antti visited a number of years ago. So Antti, we look forward very much to your talk.
Yeah, thanks a lot. Yeah, I should share the screen, I suppose. Yeah. You see it?
Yes, looks good.
Okay, so thanks, Arthur, for the invitation. It's a pleasure, and that building certainly brings back memories a lot from the old days. So what I want to talk about is Liouville theory, and I should apologize since I see some people who have heard this talk at least once, maybe many more times. It's not exactly the same talk. It evolves because the subject evolves, but anyway, there will be, unfortunately for those people, a lot of repetition. But let's go anyway. So the topic is Liouville theory, which shortly is just two-dimensional, very simple quantum field theory with the following action functional here, just the free field and an exponential of the field. And this action functional has a long history, goes back at least to the end of the 19th century, beginning of 20th, when Picard and Poincaré were uniformizing Riemann surfaces by studying the extrema of this action. It's resurfaced much later in the context of non-critical string theory by the famous work by Polyakov in the beginning of 80s. Then somewhat later it came in the context of two-dimensional gravity, like Knizhnik-Polyakov-Zamolodchikov. Later, this sort of Riemann surface interpretation was stressed by people like Takhtajan and Zograf and Teschner later. And then quite miraculously, about 10 years ago, it entered also four-dimensional quantum field theories by the work of Alday-Gaiotto and Tachikava. It also entered sort of more probabilistic subjects like the study of random metric spaces by people like Legal, Guillarmou, Duplantier, Sheffield, and Miller. And what I want to talk about is the quantum field theory aspect of this theory from the probabilistic point of view. So that will be the topic, but I will give a little bit of a background first about this 2D gravity picture, and then about the conformal field theory picture, because those will be sort of the topics we want to motivate the story. Okay, so this story starts with a paper by Polyakov in 1881, where he formulated string theory in terms of looking at the geometry on the world sheet of the string of the loop when it moves in space-time. And gravity in general, of course, we're talking here about quantum gravity, or actually not really quantum, but Euclidean quantum gravity. And Euclidean gravity, of course, is a story of Riemannian metrics on manifolds. And Euclidean quantum gravity would be some sort of probabilistic theory of Riemannian metrics and maybe other fields defined on the manifold. Let me just call them psi, and call it matter fields. Okay. Now, formally, a physicist would write then this probabilistic theory in terms of a functional integral against observable depending on the metric and the matter fields, and then some density given by action functionals. And of course, this is rather intractable in general, but in two dimensions, the space of metrics is quite simple, because modulo the action of diffeomorphisms, which of course should be invariance of the theory, the metric basically has just 1 degree of freedom. There is the metric can be written depending on the topology of the surface. It can be written as a positive function times some finite dimensional space of metrics, namely the moduli space of metrics. So when we want to put a probability law on such objects, then we are really asking for a probability law on functions on the 2-dimensional manifold, real valued functions. And so for instance, if we take an observable which depends on the metric, we would ask whether we can find some sort of effective action depending on this 1 remaining degree of freedom, so that the expected value can be written again completely formally at the moment in terms of integral over just these conformal factors. Now, answer to this question in general is not known, but if the matter field, what I put here, is a conformal field, then it is known, or let's say conjectured, of course, since this is all on the level of theoretical physics at the moment. So this was done by Knizhnik-Polyakov-Zamolodchikov, and they gave the following answer: if the matter is given by conformal field theory, which of course are described by classified by to a certain extent by a quantity called the central charge, then in that case this factor, this sigma field, is a number times a fixed field which I will call phi from now on, and the number I will call gamma. And the probability distribution of this field phi is given just by the Liouville action functional exponential of that and formal functional integral over the field phi. So that was the proposal of these people. And I have to tell you what the parameters here are. So let's go here. So KPZ said that the action functional has this form, and there is the parameter gamma which enters here, which the metric is e to the gamma times phi times the flat metric, if you wish. The parameter gamma depends on what the conformal field theory you couple the gravity to is, and the correspondence which they found is the following: if you call C the central charge of the conformal field theory, then it's connected to this gamma. The gamma which you put here depends on the C through such a strange looking relation. And there are a couple of parameters here which are repeated in the story over and over again, so let's stare at them. There's the parameter gamma, which should be positive if this is going to be a metric. Sorry, it's supposed to be real if this is going to be a metric, since the factor should be positive. So gamma is a real number, and obviously the sign of gamma doesn't matter, so let's keep it positive. And then the relation is the following: the C of the conformal field theory is related to gamma by this strange relation via the factor Q, which is gamma over 2 plus 2 over gamma. Now, if you look at these numbers here, if gamma is real, then this number here is at least 2, and the square of it is at least 4. So the C is at most 1. So that's what these people found. If the conformal field theory has central charge for less than 1, then the effective action is given by Liouville model with that these parameters. There's a cosmological constant term here. That's what this number is called. It should be positive, of course, to have stability. But it actually is not the perturbative parameter. It's not a parameter. It can be simply scaled away, as we will see later. So you can't view this as a small perturbation, for instance. Okay, so this theory was conjectured then later around the same time to be a scaling limit of statistical mechanics models defined on random lattices. So you put, for instance, an Ising model on a random lattice and study the properties of that model. So that goes back to Kazakov in the 80s. Here is a picture of one of these one of these models with a corresponding to the gamma equals square root of 2 parameter. But here is a discrete model which describes the sort of geometric object this this system is supposedly describing. Okay, so the final piece of this background story is what was called gravitational tracing, namely how does this these critical models or this conformal field theory coupled to the gravity, how do you get? I told you that the correlation, if you look at just the marginal of the law on the metric, then it's given by this Liouville action. But what about looking also at objects in the matter field? So let's, as an example, let's take a Ising spin, so Ising model on the random lattice, and so let me call sigma the scaling limit, the usual scaling limit of a Ising model. So the quantum field theory attached to that, and then let's take sigma tilde, the scaling limit of Ising spin on this random triangulation of the manifold. Then the relation is supposed to be the following. You can just compute correlation functions of this guy in terms of those by multiplying by appropriate factor of the Liouville field. Namely, in the Ising case, you take the gamma equal to square root of 3 Liouville field. You take exponential of that guy with a certain mysterious number, alpha, here, in this case, 5/2 of square root of 3. So the statement is that to get the random triangulation correlation functions, just need to compute the correlation functions in the non-random case and multiply them by correlation functions of these exponentials of the Liouville field. And similar formulae go for all these C less than 1 theories. So that's the upshot of all this story, is that from this point of view, one would be really interested in understanding correlation functions of these exponentials in the Liouville theory. So these correlation functions. So that should be the holy grail of our study. Okay. Now, the Liouville theory itself, I told you that it became as the sort of effective theory of this metric, but it itself actually is expected to be a conformal field theory. So let me give the few basic background notions from that theory. So if you think about Euclidean quantum field theory, then by the scaling limits, it's modeling statistical physics models like Ising model. And if you are at a critical temperature, such systems are expected to have conformal symmetry, not only being scaling invariance, but actually conformal symmetry. And then the corresponding quantum field theory, what you get from in the scaling limit, should be a special quantum field theory, namely conformal quantum field theory. And it turns out that this extra symmetry gives strong constraints and correlation functions via a procedure called conformal bootstrap, which we're going to describe a lot in this talk. So this approach was very much, to great extent, utilized by Knizhnik-Polyakov-Zamolodchikov in their famous paper on conformal field theories. So using this bootstrap idea, they found explicit expressions for correlation functions in several cases. And more recently, the same story has been extended to 3 and higher dimensions by Knizhnikov and many other people. So what is it about? Well, first of all, conformal invariance. Or conformal field theory, sort of in a very impressionistic terms, would be something like the following. So you have a bunch of random fields, call them random fields, scaling fields, rather, which I let's be, for instance, in RD, the fields defined on RD. So, for instance, using spin in the continuum limit, and then you have some expectation, some probabilistic notion, and you're interested in computing correlation functions of these scaling fields, and the axioms are that the scaling fields are exactly scale invariant at the critical point, and the way they scale with a power law, and the power is called the scaling dimension or conformal weight of the field. And the conformal invariance basically means that this scaling can be done in a space-time or space-dependent manner. So you can actually use conformal maps and not only scaling to do it. So in 2 dimensions, for instance, on the plane, you would have the Möbius maps, the fractional linear transformations, and then the scaling factor would be some related to the derivative of the map, to that map. Now, that said, if you are on the plane, or actually in that case, the conformal symmetry really tells you that you should be on the sphere, 2-dimensional sphere, the 3-point functions then are completely determined by this symmetry, which has 3 complex parameters in it, and its spatial dependence factoring out, there is only a constant left, which depends on what actually are your scaling fields, and that constant is called the structure constant of the conformal field theory. Now, the second axiom, so the first axiom was that we have conformal invariance. The second axiom is more maybe more long to explain, so let me just try to do it as quickly as possible. We are going to see it again later. It could be called the operator product expansion, which says that if you try to compute these correlation functions, the axiom tells you that you can replace 2 fields here, 2 scaling fields, by a linear combination of 1 by an expansion. There's an expansion where the product of 2 fields can be replaced by such a sum, where the coefficients in the sum are completely determined by the structure constants. Actually, they are linear in the system.
Can I ask a question? Is this supposed to be an exact relation or an approximate relation?
This is actually supposed to be an exact relation, and we'll see it later. But in the case where we prove, namely in the Liouville model, it will be an exact relation. You can make it as an axiom and then try to study cases where you could actually prove, find examples. And not only so exact meaning this is completely fixed by the conformal symmetry. So in that sense, this is exact. And actually, it's expected to be a convergent sum once you apply it with taste. Okay. what's remarkable in it is, of course, that it's just completely determined by the structure constants, but there is the summation index, namely what fields actually enter here, and that set of fields which enter here, so I call them the indices, but the index the scaling fields, it's called the spectrum of the conformal field theory. So if you happen to, one way or the other, to figure out the structure constants and what the sum takes, one by one you can compute all the correlation functions. That's the story of this operator product expansion. So all correlation functions are determined by the structure constants. So to solve a conformal field theory, we need to find its spectrum and its structure constants. Many of you have heard, of course, that the one way to tackle this question is the following. You could look at the 4-point function, and if this axiom holds, you can compute it either by applying the operator product expansion to the first two guys or the last two guys. Okay, and you get different relations. You get these are the sort of related to the structure constants, and so are these. So this is actually a quadratic equation for the structure constants. And actually this equation has been used to great results in, for instance, 3-dimensional Eigen model to compute critical exponents. And in 2 dimensions, many explicit solutions of the equation are known. Now, what are these solutions? And now I stick to only 2-dimensional case, which we are here doing. So basically, the solutions can be, or the theories maybe could be classified into 2 groups, sort of comparing maybe group theory, make harmonic analysis whether on compact or non-compact groups. And one could call one class of theories compact conformal field theories. They are the ones where the spectrum is discrete. So either it's finite, these are the original minimal models like Eigen model, which were found by Polyakov-Zamolodchikov, or it could be countable like the Wessumino-Witten models with compact groups. In all these cases, explicit formulae for the structure constants are known in terms of basically Coulomb gas integrals. And then there is like in the case of the groups, there is a case of non-compact conformal field theories where the spectrum is continuous. So instead of having a finite sum here, we have an integral, okay? And the one which we are going to discuss of that category is the Liouville model. There are others. There are Toda models, WZ double models with non-compact groups, but we concentrate here on the Liouville model. And in this case, the explicit formula for the structure constants were conjectured in the mid-90s by Dorn and Otto and Zamolodchikov. So we'll come back to that. Now, what would it be to do this thing constructively? Constructive field theory, quantum field theory, of course, goes back to long times. And our organizer of our seminar was one of the initiators of this business. So there one would try to find examples satisfying these axioms, the bootstrap and the conformal invariance, by doing functional integrals and making mathematical sense out of them. So you have some, in this case, you would have some fields defined on your surface, taking values, some space, target space, and then you would like to do that the correlation functions are given by some sort of integration over the set of all those fields weighted by a Gibbs factor, some action function. Now, this hasn't been terribly fruitful in the case of these compact conformal field theories. In minimal models, one expects taking the P phi 2 model, namely polynomial in the fields, and taking a scaling limit of that, you would end up to these theories, but this is very unexplicit and not leading to any calculations. In the Wessel-Miller-Witte models, the action is completely explicit, but still direct analysis from the functional integral is not so easy. Now, the Liouville case, as we will see, is quite different. So let's go back to it again. So as I said, the Liouville model, which we introduced through the quantum gravity, is actually expected to be a conformal field theory. Well, it is, that's what we prove, of course, but the conformal field theory, and remind that there we are interested in this action functional, and the scaling fields turn out to be just the ones which we sort of stumbled to in the two-dimensional gravity, namely exponentials of the Liouville field, where actually the coefficient could be also not necessarily a real number, and these are the correlation functions we would like to understand. Okay, and as I told you before, the cosmological constant is not a perturbative parameter, because basically a shift in the field phi, just you can shift it at will, and that turns out to be the case indeed. So it's not a perturbative parameter. So the only real parameter, it basically can be scaled away in all interesting cases. So the only interesting parameter is gamma. So there's this one parameter gamma, which, as you remember, hopefully was some number less than 2. Well, it turns out to be that it will be a number less than 2. I didn't explain that yet, but anyway, so here is the relation. The central charge of the Liouville model will be related to gamma by that formula, and the scaling exponents of these vertex operators are supposed to be given by these numbers. All right. Now, so the first question is, what is the spectrum and structure constants? The spectrum was actually conjectured quite early in the story, immediately after Polyakov's paper, and it goes back to Cartwright and Thorn, and they conjectured the spectrum is continuous and given by these vertex operators, so exponentials of the field with a very particular weights, q plus ip, where p is a real number. We'll come back to that later, but that's sort of the expectation. Structure constants, what are they? So actually, Polyakov viewed as the whole business of conformal field theory as just a formalism created in order to study the Liouville model originally, and to his distress, this didn't actually lead to calculation of the structure constants, so Liouville field theory. But this was remedied somewhat later in the mid-90s by Dorn and Otto and Zamolodchikov, who proposed really very remarkable formula for the explicit formula for the structure constants. And just to show you that such a formula exists, here it is. It's called the DOZZ formula, Dorn, Otto, Zamolodchikov formula. And it's basically a formula which where, of course, all the alphas enter, the gamma enters, and the cosmological constant enters. And apart from that, there is a special function which is related to the double gamma function, or the Barnes G function, if you know what that is. So it's a very rather complicated special function which enters in a rather non-trivial way. It's actually a meromorphic function of these alphas, and it has simple poles on the real axis and on set and discrete set. Okay, so that was sort of the story from the history of this model. It was this formula, of course, was a conjecture, and it was checked numerically to solve the quadratic bootstrap equation. So no doubt it has a chance to be the correct formula. And if you use that as an input, the Cartwright-Thorne spectrum and this formula, then you would have an explicit formula for the 4-point function. I remind you that how did you do it? You just did the operator product expansion to these two guys, and then you ended up to a quadratic relation. And that relation, once you apply it explicitly, I didn't tell you exactly how the explicit thing goes, but once you do it, the end result is the following. You have the DOZZ structure constants, two of them. They depend on the spectrum parameter, which was this Q plus IP. You integrate over because now you have a continuous spectrum. There are some scaling factors which are should be there. And then there is a purely representation theoretic object called the spherical conformal block. So it's completely determined by the conformal symmetry, and it depends on the various parameters here, namely the alphas and the P and the central charge of the Liouville model. Okay, so those are the two conjectures. And what would it be now that for constructive theory? We should give a mathematical meaning, first of all, to the functional integral. We should prove that indeed the 3-point function is given by this fantastic formula. Then we should understand what is the spectrum, and then prove the bootstrap formula for the 4-point function, and indeed similar formulae for the endpoint functions, as well as in general on Riemann surfaces on arbitrary genus. So that's the sort of story I want to now try to describe. Let's first start with a probabilistic formulation. So what is the mathematical meaning of this integral? Of course, this was just the story which was started by constructive field theory in the end of 60s. And such functional integrals were typically made sense by viewing them as around a Gaussian theory, namely the quadratic part here. So in this setup, let's now work on arbitrary surface. So sigma is a two-dimensional surface, and G is a Riemannian metric on it. So we have a Riemann surface and a metric on it. And then you can do free field. There are many ways to describe free field. Let me just give you one as a random eigenfunction expansion. So you take the Laplace operator. That's really what is involved here. The Laplace Beltrami in that metric, and it has a discrete spectrum and eigenfunctions, which I can enumerate from 0 to infinity, and do an expansion where the coefficients now put random numbers as independent random variables as coefficients. Scale, do a little scaling with the eigenvalue here, and then the coefficient xn are just independent identically distributed normal random variables. Okay, just standard Gaussians. So that's a random function. And then the Liouville field here, you take the phi, just this random function plus a constant, namely the one which is, there's one eigenfunction which corresponds to the constant, the 0 eigenvalue, which is not in this expansion here. So I take it separately. It's not a probabilistic object like the rest. So it's the 0 mode, the constant mode of the field. So that's the definition of the phi. Okay. So that takes care of this d phi and this piece here. I still have to understand this guy here. That's also rather standard story of the old constructive quantum field theory, maybe with a slight twist. So the Gaussian free field, the one which I defined here, is actually not a function, it's a distribution, because it's really the 2-point function is given by the green function of this Laplace operator, so it has a logarithmic divergence at coinciding points. So in particular, the variance of the field is infinite. So to define it, one has to renormalize it, and of course, this is well known how this is done. You regularize it by smearing it out on some scale epsilon, and then you renormalize it by weak ordering, namely multiplying this guy by a constant which goes to 0 as the regularization is removed. Now the only slight variance here with respect to what was done in constructive field theory in the old days is that in what sense does this weak ordering converge? So actually you should view it as a measure. So the weak ordered exponential, think about it as multiplied by the Riemannian volume of your manifold, and view that as a measure, and then integrate it against the, say, continuous function, for instance. Then this is a random variable, and that random variable converges in probability. And to an integral over a random measure, and that measure was in probability. It was called. It was introduced by Kahan in the 80s, and it was called the Gaussian multiplicative chaos measure. So the exponential, the weak ordered exponential, viewed as a measure. It's an interesting probabilistic object per se. It has multifractal. It's a multifractal measure. It's not absolutely continuous with respect to the Riemannian volume. It has multifractal in the sense that if you look at volumes of balls, for instance, in that measure, they have a non-trivial scaling. So the Bth moment scales with some relation, which is actually explicit here. And maybe slightly surprising even to people who were doing these things in the constructive field theory times, is that this measure actually is identically 0 if this gamma parameter is too big. Actually, if it's 2 or more. If you remember, the gamma was related to the C of the conformal matter, which we could couple to gravity, and gamma less than 2 here means that the conformal matter can be at most C equal 1. So anyway, so this is a nice probabilistic object, and we can define the Liouville functional integral now as follows probabilistically. So you take some suitable observable of the field, then the expectation value is defined as follows. In place of the field, you put this constant and the Gaussian free field. You weight it by exponential of the multiplicative chaos of the whole universe. And then there is, of course, e to the cosmological constant. And since the field is really C plus X, then there is the e to the gamma C. And the only thing which you have to be a bit careful once you are on a surface with a non-trivial topology, as we are typically, then there's a term coming from that which couples to this constant mode. So there is an exponential factor in the constant mode which we are integrating over, and that's proportional to the Euler characteristic of the surface. Okay, 2 minus 2 times the genes. So that's the probabilistic definition of the Liouville model. Okay. As the correlation functions can be also defined in the same way. I mean, you regularize the vertex operators and take limits, and I won't go to that. It's basically the same story. Okay, so that's stated. When do they exist? So this is where we started our work on this subject 5 years ago, 6 years ago, by François David, Rémi Rod, Vincent Vargas, and myself. So when do these correlation functions actually exist? They exist if and only if two conditions hold, namely the alphas are not too big, and their sum is not too small. The second condition we can easily understand if we look at this integral. I'm supposed to integrate over the c variable. Where does it enter? Enters here and here. Well, here it enters in the exponential. So as c goes to plus infinity, this damps a lot. So this looks like okay. Whereas when c goes to minus infinity, this gives no weight whatsoever. And this could blow up, especially once I have the vertex operators, which also couple to the c. So I need to have convergence in the c going to minus infinity, and that's the reason for this bound here. The second bound is more subtle. It deals with the multifractal properties of this multiplicative chaos, and I think I will skip that explanation here. Rather than say more about that, let me just say that once we have shown they exist, they have well-defined probabilistic expressions, and actually the C integral can be explicitly done. And for instance, for the structure constants, you can write it as an explicit expected value of a random variable, which is related to this multiplicative chaos measure. So the structure constant of the Liouville theory, as defined in this story, is an expected value of a moment of a random variable where you integrate over the multiplicative chaos of a function which has singularities at the point where the vertex operators enter. And the fact that there are these singularities leads to the fact that the alpha shouldn't be too big for this integral to make sense. And this is an expression which you could put to computer and compute. And the question is, does it satisfy the probabilistic formula? And the short answer to that is that it does. And that's what we proved with Rémi and Vincent some time ago. Namely, if these alphas satisfy the probabilistic Seiberg bounds, then the structure constant as defined here, this probabilistic definition coming from the functional integral, actually agrees with this formula which was conjectured by DOZZ in the 90s. Now, the proof of that is a long story. It combines a lot of probabilistic analysis of the multiplicative chaos. But in the end of the day, since you want to get the formula, you have to do something more. And you use this analysis to derive algebraic identities to the structure constants, which in the end determine them uniquely. And this is an idea which goes back to Teschner in the 90s. Maybe I will not say more about that at this point. And let's go to the 4-point function. So let's still be on the sphere, two-dimensional sphere, as in the structure constant. So let's look at the 4-point function. And it has, again, a probabilistic formula very similar to the 3-point function. So there are some factors, don't worry about them, but it's again a multiplicative chaos now integrated against the function which has singularities at these 3 points, at 0, z, 1, and infinity. By Möbius invariance, you can fix again up all the points except one and get an expression which again could be put into computer and computed. Question: can we express it in terms of 3-point functions? Answer: yes. That's what we proved last year. The alpha I, if they satisfy again the Seiberg bounds, which is necessary here in the probabilistic setup, then indeed this 4-point function is given by such an integral, where the DOZZ structure constants enter. There is a purely representation theoretic factor, as I said before, called the holomorphic conformal block. And apart from that, you do an integral over the spectrum, which is basically just one real variable here. Now, the proof of this is again a long story, but to make it short, the story goes by expressing the correlation function in terms of a Hilbert space picture as a scalar product. And once you write it as a scalar product, then you try to factorize it by using basically spectral resolution. And spectral resolution of what? Well, of the Hamiltonian of the quantum field theory, which you have to study. And then all the representation theoretic business should come then from the conformal symmetry and from conformal ward identities. So maybe I go to that a little bit in a moment, but let's just state how it looks in general. So this is something what we are presently doing. So the bootstrap can be actually carried out in complete generality. So if you look at the correlation functions on a Riemann surface in general, there is a similar relation. So for instance, if you take an endpoint function at the sphere, you would get such a formula, or the torus or higher genus. So it would come as an integral again, where you have, instead of the one spectral parameter here, you have a lot of them depending on the genus of your surface and the number of insertion points. You're integrating over them. The result depends on the basically moduli of your surface, and it becomes as an integral of a holomorphic function of those moduli squared, which are conformal blocks. And again, the integration measure involves product of structure constants, and the way we do this is formulating the Liouville functional integral. You can set up put these functional integrals into pieces. This is a approach by Graham Siegel to conformal field theory, which goes back also into the 80s, where he envisioned by building conformal field theories by gluing things related to building blocks of Riemann surfaces. So Riemann surfaces you can build by gluing pairs of bands, annuli, and disks to each other, and then there are objects in the conformal field theory which correspond to those objects, namely functional integrals over on those surfaces with boundaries, and then you glue these guys together using the spectral resolution of the Hamiltonian. So that's the way we end up to formula like that. So maybe I don't know how. Maybe Arthur, you want me to stop already now, or shall I still continue? 5 minutes. No, I think I've spoken at 50 minutes.
You can go on, but if you have more to say, go ahead.
Okay, I'll say a few words. So maybe.
But this was exactly what I was about to ask you.
Okay, all right. So how does the gluing go? Where does this gluing come? So let's go to the simple case of the 4-point function of the sphere. it comes, of course, from reflection positivity. The Hilbert space, again, all this story, you should, if you want to learn, if you're not familiar with it, there is a nice book by Lim and Jaffe from the 70s, where this is explained in very clearly, and applying this procedure, which goes basically to Osterwald and Schrader in the early 70s, is called reflection positivity. So how do you get quantum field theory out of probabilistic field theory? You have to reconstruct Hilbert spaces and Hamiltonians, and the way you do it is in this setup, which is called in physics radial quantization. You view sort of the quantum Hilbert space will live on the circle, the equatorial circle of the sphere, on the sphere. So think about the radius vector on the plane as exponential of time. So time is sort of logarithm of the radius. And you take Hilbert space, all the functionals of the fields which depend on the fields only in the unit disk. Okay. So put the vertex operators, say, in the unit disk, for instance, arbitrary many of them. And then how do you get the scalar product? Well, there's a natural operation here. You can reflect complex numbers, of course, from the unit disk outside to the exterior region, which is also a disk on the sphere. And this reflection naturally transports observables from the disk to outside. So if you take two observables in the disk, you can form a scalar product just by taking one in the disk and one reflected, and then you check that this actually is a scalar product. So that's the story made extremely short. And so there's a new positive object here. There was the expectation in the original Liouville model, but there is also a positive Hilbert space scalar product.
And can I ask a question? On what type of Riemann surface can you prove this?
Okay, here I'm doing everything on the sphere because we are.
But have you looked at the Riemann surface problem?
Yeah, sure. Yes, I mean the gluing is really once you formulate it on the general surface, it goes along these lines. Basically, if you take a surface and you take a boundary circle and integrate over the fields elsewhere, you get the state in this Hilbert space here. So that's how it goes. To make a long story.
You have to assume a reflection invariant surface.
No. Okay, so the 4 point on the sphere, of course, we are on the reflection invariant. So on the sphere, this becomes just a simple object, the 4-point function. It's just a scalar. If I take 2 points, say in the disk and 2 outside, then these are reflected from the inside, and I can write it as a scalar product. And then the bootstrap is just obtained by factorizing this thing by spectral resolution of the Hamiltonian of the Liouville model. So just to say what that is, still going back again to the textbook of Lim and Jaffe, and the idea going, of course, back to Osterwald and Schrader and earlier. So there is a natural operation here, namely in the observables, namely the dilation by numbers less than 1 map the unit disk to itself, and that extends to this space of observables defined in the unit disk, and it gives rise to a semigroup there. So that's a completely general setup, and that turns out to be a contraction semigroup, and the generator of the semigroup is a Hamiltonian, quite generally. And in the Liouville model, that's the attitude we take. We construct this Hamiltonian. It's a positive self-adjoint operator, and we need to study it because we want formulae. So we prove that it has a continuous spectrum and a complete set of generalized eigenfunctions, which can be actually constructed by using scattering theory. And then the spectral states can be organized into Virasoro algebra representation modules. So that's made really short a long story. That's the reason how this formula comes about. You write this as a scalar product, you insert there the spectral resolution of the Hamiltonian, and you utilize the conformal symmetry. Now, I don't think I want to go more to the details, except maybe to say just one word: why does spectral theory enter here? Namely, this is the general setup, but of course, practically everybody who has studied quantum field theory, and again, you can read it in the textbook, you can realize this Hilbert space in the usual way as a Fock space, namely by looking at just functions, fields defined on the time zero, which is the unit circle here. And you get the Hamiltonian concretely by a free field Hamiltonian plus a free particle, and then the Liouville potential entering into the as a interaction term in the potential. And what we need to do is to diagonalize this Hamiltonian, find all the eigenfunctions. And just what it has to do with scattering theory, if I just completely ignore everything except the zero mode, there's a free particle, and then there is an exponential potential. So the Schrödinger operator in the zero mode, in the constant mode. And this is a simple Schrödinger operator. It's a potential which goes to infinity at plus infinity and to zero at minus infinity. So you can find its generalized eigenfunctions just by scattering theory, by sending a plane wave from minus infinity. It gets reflected back to and returns back with some reflection coefficient. And this is the intuition what we apply to the Liouville model. And of course, what we need to do is to do the free theory at minus infinity and then scatter it back to plus infinity. And that is then a longer story, and maybe I will not talk more about that unless somebody wants to hear more about it. And then there's a story of the Riemann surfaces, which maybe I skip also. So just to finish, this is a nice model from the point of view of constructive field theory because it's super renormalizable, so it's quite simple, but it has global aspects, which makes it extremely non-trivial in the end in structure. And nevertheless, you can sort of, using functional integrals, get to the structure. So that makes it as a nice model where you can actually carry out this whole bootstrap philosophy to the end. Now, as far as understanding what is really connected to, there would be interesting questions which we don't understand at the moment. So certainly one interesting question is that, and that has been the major open problem of Liouville model ever since it was introduced. How do you go beyond this gamma equal to this restriction what we had here on the value of the gamma? So this is the obstacle to non-critical string theory. This is the obstacle to many things. This is also related to getting analytic continuation in gamma. You expect to get from the Liouville model to other conformal field theories. So that we don't know how to do. Also, how is it connected directly to the scaling limits? That remains a conjecture. How is it related to these Liouville quantum gravity metrics, which have been recently constructed by people? Similar story can be done to Dodaf conformal field theories, but there are some questions there where one can't go as far as in Liouville. And then there are other non-compact models where one might have some hope for success. So I think there are interesting things for constructive field theorists still to do here in this subject, and maybe I close with that.
Well, thank you, Antti, for a really beautiful lecture. You summarized a lot of material, and the new work, the 2020, and you have some other paper beyond, are they published or on the archive?
2020 is on the archive. This is on the archive, and this we are working on at the moment.
So I'd like to open up the floor for questions. I'm sure there's going to be a great deal of discussion. We have quite a few experts here.
Yeah. So thanks a lot. Coming back
to your microphone is a problem, so back off.
Warum? Warum ist Mikrofon ein Problem? Otherwise to listen.
Okay, does this work?
No,
yes.
Better, yeah.
Yeah, okay. Do you have a partition function for the torus? I mean, a function, the dependence on the moduli?
On the torus, the first, the partition function is infinite. So the first non-trivial is the one-point function. So we have explicit formula for that, yeah.
Yeah. So if the partition function is infinite, what is the physical interpretation of the module?
Well, I mean, on the sphere, it's also infinite. I mean, on the sphere, the partition function is infinite, one-point function is infinite, two-point function is infinite. The first non-trivial function is the three-point function because of these Seiberg bounds. So this is a quantum field theory where the SL2 invariant state is not in the spectrum. Let's put it like that. But it's a completely well-defined conformal field theory. I mean, but partition functions don't have to be finite in conformal field theories. Of course, on the sphere, all the correlation functions except the first two are well defined, and on the torus, starting from one-point function and genus 2, the partition function is already finite.
Yes, well, my question is rather, what would be a physical system for which this situation makes sense?
What would what do you mean by a physical system? I mean, this is I mean, this is a quantum. This is a.
I think he's asking the question as to whether this is the scaling limit of a statistical mechanic problem.
Right. Well, I don't think a Liouville model, you should think about it as a statistical mechanics model. I mean, in the statistical mechanics thing where one is looking at the random spin systems on random surfaces, then this is sort of an auxiliary theory which enters into that business, and the fact that it doesn't have all the properties we usually have on conformal field theories is not. It's just that's how it is. I mean,
I wanted to ask about the analytic continuation in gamma.
Yeah.
I guess it means that your constructive method will not apply in that case once you're outside your bound.
Right. So if you look at the DOZZ formula, then it's, as I told you, it's a meromorphic function of the alphas, but it's also analytic function of the gamma. So in DOCC formula, you can continue in gamma everywhere, and
Yeah.
people have been doing that and relating it to Potts models and this and that. Okay, but in the functional integral, even the alphas a priori should be only real. But what we prove is that they actually are analytic in alpha, and you can analytic continue in alphas. But in gammas, we don't know how to do that.
But
So,
you presumably lose reflection positivity in both cases.
yeah, reflection positivity, but I mean that's it's even more severe when if you try to put gamma away from real axis, then you are using stability of the functional integral, and it's just not obvious at all how to define this thing probabilistically. It's e to the gamma phi, so put a little there, then you are in trouble immediately. And we could overcome that problem in the case of the vertex operators, but not in the case of the Liouville. So we don't know what to do with that, but that certainly, one should expect there to be analytic continuation in gamma, and it certainly should be there, but how to get to it, I don't know.
Your formulas for C in the relation with gamma at the beginning of your talk, it certainly reminded me very much of the type of thing that comes up in Jones' theory. And I wondered if there's any relation between the index and the values of the gamma.
You mean in Jones' theory, more specifically, I mean, what?
The index theory.
Okay, I'm not, maybe somebody in the audience.
Maybe Andrea Chengwei maybe can comment.
I don't know.
Somebody is talking, but they're on mute or it's not coming through.
Now
is that now good?
Yeah, now it's
Okay.
good. Yeah.
Okay. If I understand correctly, gamma is the parameter that controls the central charge. Is that right?
Yes, yes.
So and the wall that you're hitting is the special value c equals 1. Is that right?
Yes, in the matter. So in Liouville, it's the c equal 25.
Oh, I see. In the Liouville is c equals 25. So you can only deal with c bigger than 25 or c smaller than 25.
Only bigger than 25.
Only bigger than 25. I see.
Which means that the matter has to be less than 1.
I see. Okay. Thank you.
Unfortunately, I mean, this is the eternal problem, and it's certainly not resolved here.
I'll add something. To go back to this complex gamma and so forth, I mean, there were these absolutely ancient results like late 80s by like Hollywood and Mansfield and Iguchi and Yang, who claimed that imaginary Liouville with imaginary gamma correspond to the minimal models, no gravity, just plain old Liouville. And then I'm not sure how useful that statement was for the pure CFT, but what was nice then, when you did an off-critical perturbation, you added the e to the minus I or gamma type thing, and then you would get sine Gordon, and this connected sine Gordon to integral perturbations of minimal models. But I think it's fair to say nobody, even though this was used at least heuristically for many things, no one ever really made any precise sense of this. But now, since you have some control and continuing in gamma, might you be able to make sense of some of these claims?
Yeah, I mean, exactly. These are really intriguing. Of course, again, people just continuing in the DOS formula, you can do this going to the imaginary gamma and then get the connection to the minimal models, and it doesn't. There are ways it goes through and it doesn't go through. Okay, but as far as the sine Gordon, I think that's really interesting. There's a simpler model than sine Gordon, which is integrable, namely the Sinch Gordon. So
Yeah, I was going to say, I think it depends on your point of view, which is simpler or not.
Well, from this point of view, analytic
Yeah,
continuation.
I was going to say from all the traditional methods, sine Gordon is a lot nicer than Sinch Gordon.
Exactly, but here it's Sinch Gordon. You know, I mean, there are nice formulae actually for the Zamolodchikov and these people. They have nice formulae for the one-point function, for instance. Not so very different from, I mean, sort of intriguingly close to the kind of formulae which we see here. And of course, Sinch Gordon you can define because it's just e to the gamma phi plus e to the minus gamma phi. So this is completely well defined. It's of course not conformal field theory, but you can do many things with that probabilistically. And an interesting question would be to see if some of these formulas, those formulae could be uncovered. But again, I have nothing to say about that except that I would recommend people looking at it. And of course, sine Gordon is more interesting model and more intriguing, but more challenging also from this point of view.
Good, thanks.
So are there any other comments? Such a collection of experts here, I'm sure there must be something else.
Well, you've been able to prove some existing conjectures. Can you prove anything new?
That's a good question.
Very good question, John.
Let me say, for instance, just from the purely mathematical point of view, these conformal blocks on for endpoint functions, even the usual spherical conformal blocks, there are no proofs actually that this they are series expansions in the parameter z, and there are no proofs for their convergence actually. There are recursion relations by Zamolodchikov to compute the simplest ones, but once you go to higher point functions, basically nothing is known about them. Actually, we can prove that all those series converge almost surely in this parameter values which enter them. So there are some new results from that point of view, but you might not call it a physical result, but anyway.
Well, I'd like to thank you again, Antti, for a very beautiful talk and interesting discussion. And we look forward to the next paper. And also next week, we'll be back here again and Søren Popa will speak on a mathematical topic. So see you then. Bye-bye.
Okay, thanks, bye-bye.